In this last section, we're going to be looking at improper integrals. Now, all of the integrals that we've looked at so far, we haven't been able to call improper because it's the limit of integrations that make an integral improper. So a couple different ways that we could have an improper integral. First of all, we could have some limit of integration that's infinity. So we could be trying to integrate f of x dx from 0 to infinity, or let's say negative infinity to some constant 4 f of x dx. So basically we're saying that infinity is involved in one of the limits of integration. Now it could be positive or negative infinity, but that's one of the things that can make an integral improper. It's a definite integral that involve our limits of integration at infinity somewhere. Now another thing that could make an integral improper is if I have a discontinuity across the limits of integration. So for instance, I could be trying to integrate something, let's say like 1 over x minus 2 dx. Well, let's look at a quick graph. It's nice to be able to look at a graph here of 1 over x minus 2 dx. I have a vertical asymptote here at x equal 2 because the fraction is undefined at 2. And then basically my graph looks like this on either side. So if I look at this and I have to integrate across this vertical asymptote where the fraction is undefined, there's a discontinuity involved. So definitely have a discontinuity. In this particular case, I have one at x equal 2. So if I was trying to integrate and I went from, let's say, 0 to 4, I would have a problem because I'm going across where the function is undefined. So there are a couple different ways I deal with this. First of all, I could split this up into two integrals. I could integrate from 0 to 2, and then pick up again from 2 to 4. And that would help solve the problem. And you might say, well, wait a minute, it's still undefined at 2, so what do you do? Well, what you do is you take a limit as x approaches 2. In this particular case, if we think about the number line, I'm going from 0 to 4, and 2 is right in the middle. So as I'm going from 0 to 2, I'm approaching 2 from the left. And as I'm approaching from 2 to 4, I'm approaching 2 from the right. And so really that's what we're getting back into, is the idea of limits here. So those are two different ways we can have an improper integral. Now I'll show you what to do with each of these, but there's a couple of other things that we need to look at first. Let's review limits real quick. Limits at infinity we had some particular rules for. So my first one, and again I should put limits at infinity here. If I'm taking the limit as x approaches infinity or negative infinity, and I have an expression, a rational expression here, where the degree in the numerator is less than the degree in the denominator, this limit as x approaches infinity is going to 0. This is my shortcut rule. So for instance, we could have limit as x approaches infinity of something like x squared over x to the 5th. Now both the numerator and denominator are going toward infinity. The denominator is going faster and basically overtakes this numerator, so that's going toward 0. Now how would you justify this? Well, you could divide through by the highest power of the exponent in the denominator. You could simplify and cancel, or you could just write off to the side. This works because the degree in the numerator is less than the degree in the denominator. Another shortcut rule, so here's one of them. Here's another one. Let's look at the limit as x approaches infinity. And we could look at negative infinity here as well. If the degree in the numerator is greater than the degree in the denominator, this is going toward infinity. Now, the last time we looked at these were in terms of horizontal asymptotes, so those still hold true about a horizontal asymptote not existing here. But this is going toward infinity. So if we wanted to look at a specific example here, and again this could be negative infinity as well, we could have something, let's say, like x to the 5th plus 2x all over x squared plus 1. Now both of these are going toward infinity, but the numerator is going faster toward infinity, so this overall fraction goes toward infinity. And how do I justify it? The degree in the numerator is greater than the degree in the denominator. Now if you wanted to, you could go through the whole process of dividing through by the highest power of the exponent in the denominator. You could also look at this in terms of trying to factor and simplify. All sorts of different things there. Now this is interesting. This is going toward infinity. So in terms of improper integrals, what this means is it diverges, the integral diverges. That means it doesn't go toward a particular value, it's going toward infinity. Now over here, since this is going towards 0, we would say that this converges. Okay, so we have one rule left. We have less than 0, or sorry, less than, greater than, and then what if they're the same? Limit as x approaches infinity, and of course this would work with negative infinity as well. You just have to watch out for the powers. What if the degree in the numerator and the degree in the denominator were the same? Well, this limit is the ratio of the leading coefficients. So that's what I have going on here. The ratio of the leading coefficients. Okay, so shortcut, limit as x approaches infinity, and we could also use negative infinity here as well. Let's say we have something like x to the 4th plus 3x squared minus 7 all over 7x to the 4th plus 1. Well, I look for the highest powers. In this case, it's my 4th powers, and I look at the coefficient. I have a 1 and I have a 7. So this is equal to 1/7. And how do I justify it? The degree in the numerator equals the degree in the denominator. So this would be an example of a convergent solution or a convergent integral. So we have to be careful about how we write this. Remember, if these were odd powers and this is going toward negative infinity, I'd have to double check things to make sure my solution wasn't negative. But this is kind of just a quick review or overview of limits. Now we'll run across other limits as well. We've also talked about the idea of converge and diverge. So whenever you get a solution, an actual number, then it's a convergent solution. If it's going toward infinity or negative infinity, it's divergent. And so when you're working with an improper integral, you need to make sure that you state what our conclusion is, whether it's convergent or divergent. Now we have all of our techniques of integration that we have at our disposal. But the trick comes in when we're evaluating these. Now a couple of other things. If you have multiple discontinuities because you have infinity and a discontinuity, or two different things that make it improper, what you want to do is rewrite and separate these, and so it only has one, basically we only have one impropriety in that particular integral. So we can use any techniques of integration that we have so far. So our focus is definitely on integration, but probably more on evaluation here. So let's go ahead and look at some examples. Let's look at the integral from 2 to infinity of, let's do something like 1 over x squared dx. Now I do have a discontinuity here at 0, but if you notice, my integral, my limits of integration do not cross 0. So this is improper because I have this limit at infinity. So what I do is I integrate this and then I'll evaluate it. So I'm going to pop this up top, and then after it's popped up top, I'll integrate it. Don't forget to integrate these. So we'll add 1, divide by the sum. And now I'm going to evaluate this from 2 to infinity. So now we always go upper minus lower. Now a couple things I want you to keep in mind here. I can't plug infinity in here. So quick note, do not write -1 over infinity. Don't write that, because I can't plug infinity directly into an expression. What I need to do is I need to write this as the limit as x approaches. Now we're approaching infinity. Now if we had to choose, I'm approaching infinity from the left if it becomes important. On this one it doesn't. Of -1 over x. And I can see here that the numerator is fixed, the denominator is increasing without bounds, so this is going towards 0. Quick shortcut, the degree in the numerator is less than the degree in the denominator. So far this is going towards 0 for my upper. So for my upper I have 0. So here's my upper minus my lower. So I plug in that 2. So for this piece, this is going towards 0 minus a negative is the same as a positive. This is 1/2. So therefore, because this is a number, it's not infinity, this is convergent. So if you have an improper integral because you have limits at infinity, or if you have an improper integral because you have a discontinuity, make sure at the end you comment on whether it's convergent or divergent. So again, improper integral, it's improper because I have a limit at infinity there. On our next one, let's look at negative infinity as one of my limits of integration. Let's go to negative 27. The integral that I want to look at is 1 over the cubic root of x dx. So the first thing I want to focus on is whether I need to rewrite this. This integrand right here does have a discontinuity at 0, but notice my limits of integration do not cross over to 0, so I don't have to worry about rewriting this. So I'm going to set this up in order for me to integrate it. So this pops up top, negative 1/3 dx. When I integrate it, I add 1 divided by the sum. Negative 1/3 plus 3/3 is 2/3. So x to the 2/3 divided by 2/3 is the same as 3/2 x to the 2/3. Now I evaluate this from negative infinity to negative 27. And again, don't just pop a negative infinity in here. That doesn't make sense. We have to actually think about the idea of a limit. So when we evaluate these, it's always upper minus lower. So I'm going to have 3/2 negative 27 to the 2/3. So there's my upper. And then I'll have my lower, minus 3/2. And I guess I could put the limit out front. I was going to just pull the coefficient out front. So the limit as x approaches negative infinity of 3/2 x to the 2/3. So for my first piece here, I have 3/2. Now this kind of was a big deal in the test. A lot of people missed simplifying an expression like this. What you need to do is take the root first. The 3 in the denominator means cubic root. So if you wanted to think about it, this is the cubic root of a negative 27, and then it's squared. So this is 3/2. The cubic root of negative 27 is negative 3 squared. So I have 3/2 times 9, 9 times 3 is 27/2. Now I need to come back up here and get caught back up. Now here, the limit as x approaches negative infinity. This one's not quite so interesting. If I have a negative infinity here, as x is approaching negative infinity to the 2/3 power is still going to be an infinity. It turns out to be a positive here because I'm squaring a negative. Infinity times 3/2 is still infinity. So this is basically 27/2 minus infinity, which is equal to negative infinity. That's my solution, but what I need to say here is therefore this definite integral diverges, meaning the area is going toward infinity, or sorry, negative infinity if it's below the axis here. And you could do a quick curve sketch here to figure out what's going on with that. So this is divergent, and so you could say diverges or divergent, either one here. So the integration can be pretty tricky sometimes. So far it hasn't been, but then we need to focus on evaluating these. And remember, it's the concept of a limit. This next one I really like because it involves inverse trig functions eventually. It doesn't look like it off when we first start off the bat, but it quickly turns into an inverse trig function. So this is e to the x over e to the 2x plus 16 dx. Now what we'll want to do with this one, this looks like a u squared plus a squared. So we'll want to rewrite this. So natural log of 4 to infinity are still my limits of integration, but I want to rewrite this. So this would be e to the x quantity squared plus 4 squared dx. So we'd let u equal e to the x, and it's really the e to the x down here that's in the denominator. Du is e to the x dx, which is our 1 in the numerator, and a is equal to 4. So this fits the form inverse tangent. So this is going to be equal to 1 over a inverse tangent u, which is e to the x, over a. And this is what I want to evaluate from the natural log of 4 to infinity. So again, this fits the form 1 over a inverse tangent of u over a. So the integral of 1 over u squared plus a squared du fits that form. So that's a good one to know. I'd have those three, the inverse tan, inverse secant, inverse sine, on your note card for the exam. That'll come in handy. Okay, so for my first, my upper, I'll have the limit as x approaches infinity of 1/4 inverse tangent of e to the x over 4. So there's my upper minus my lower, 1/4 inverse tangent of e to the x. X in this case is the natural log of 4 all over 4. Okay, so as I'm looking at this, for this first piece, as x approaches infinity, e to the x is going toward infinity. So basically what this boils down to then is 1/4 inverse tangent of infinity. So because as x goes toward infinity, e to the x divided by 4 goes toward infinity as well. Okay, minus 1/4 inverse tangent. Now when I have an e to the ln of 4, this base of e and the ln essentially cancel, and I'm just left with 4 over 4. 4 over 4, of course, is 1, so let me rewrite that. And then I have two inverse trig functions here to work with. So let's look at the inverse tangent of infinity. This means what angle in the interval from negative to positive pi over 2 has a tangent that approaches, it doesn't equal infinity, it approaches infinity. And the answer there is pi over 2, and I'll explain why that is in a moment. Next one is inverse tangent of 1. What angle in the interval from negative to positive pi over 2, points not included, these are parentheses, has a tangent of 1? And the answer there is pi over 4. And I don't really like how I wrote this. It makes me uncomfortable to just stick that infinity in there. So I still want to think about this as approaching infinity. That makes me feel a little bit better. It's not good math notation, but it gets across the idea that it's approaching infinity. Now why is this pi over 2? Remember, this is a limit. So if we talk about the tangent graph, the tangent is undefined, sine over cosine, wherever the cosine is equal to 0. So this has an asymptotic line at pi over 2 and has another asymptotic line at negative pi over 2. So this is what the tangent graph looks like. So what angle in this interval that you see right here from negative to positive pi over 2 has a tangent that approaches infinity? So as this is going up and up and up, it's approaching infinity. What angle is that getting closer to? And the answer is pi over 2. So that's where that comes from. These are good ones to know. These are the nice little problems that can show up easily on a handwritten homework or a test. Okay, so what we have here then is 1/4 times pi over 2 minus 1/4 times pi over 4. So I end up with pi over 8 minus pi over 16, which is 2 pi over 16 minus pi over 16, which is pi over 16. So there's my solution. Now one thing I forgot to write here is this is convergent. So this is an example of convergent. So I really like these that get involved in that inverse trig function. That's pretty exciting, especially when we have limits at infinity with an inverse trig function. Okay, let's go ahead and look at one more where we have limits at infinity. Let's look at the integral from 4 to infinity of x over x plus 2 quantity squared dx. Okay, so this one, I have this x left over at the top. Can't separate the denominator, so let's try this one. Let's let u equal the denominator, the x plus 2 without the quantity squared. My du then would be dx, but I'm left over with an x, so that tells me that change of variable comes into play here. So if I solve for x, I end up with u minus 2. So as I rewrite this, the x is u minus 2. I'm curious about something up here. Yep, that's right. Okay, so the x is u minus 2. X plus 2 is u, so this is u squared du. Du and dx are the same. And then what I do is I separate this into two different integrals, u over u squared, so I'm separating the numerator basically. Minus 2 integral 1 over u squared du. 1 over u du minus 2 integral u to the negative 2 du. So this is natural log absolute value of u minus 2u to the negative 1 divided by negative 1. So negative divided by negative is a positive. The 2 doesn't flip, but the u does. I guess I'm not ready to evaluate this yet because I need to turn around and sub back in. U is x plus 2 plus 2 over x plus 2. Now I want to evaluate this from 4 to infinity. So remember, we're taking limits. So this first one would be the natural log limit. Let's do the limit first. The limit as x approaches infinity of the natural log of the absolute value of x plus 2 plus 2 over x plus 2. So I'm taking the limit of this entire expression. So that's my upper. And then let's plug in my lower. Natural log of 2 plus 2 plus 2 over 2 plus 2. So my upper and my lower there. So this one looks easier. Let's do this one. So minus natural log of 2 plus 2 is 4. The negative distributes. So I have minus 2 over 4 is a half. Now this piece, this is interesting. So the limit as x approaches infinity of this expression, as x approaches infinity, I'm looking at the log as x approaches infinity. So remember what that log graph looked like, just real quick. As x is approaching infinity, y's are approaching infinity. Now I know I have this shift with the x plus 2, but it's the same general shape. So this piece right here is going toward infinity. And then this piece right here is going towards 0 because the numerator is fixed, the denominator is increasing without bound. So the real overall fraction is going towards 0. So the degree in the numerator is less than the degree in the denominator. So it looks like to me I have infinity plus 0 minus natural log of 4 minus a half. This is still equal to infinity, so therefore this is divergent. So if any part of the solution goes toward infinity or negative infinity, the overall expression is divergent. These last two problems will be improper integrals because they have a discontinuity involved. So for our first one, let's look at, and this one's not even improper. This is just a definite integral that I want to look at. So let's look at the integral from 1 to 2 of 1 over x to the 4th dx. This is a nice straightforward. I would have a discontinuity here at x equals 0, but the limits of integration don't pass through 0, so I'm good to go there. So this would be the integral from 1 to 2 x to the negative 4th dx. So we'd add 1, divide by the sum. So this is negative 1 over 3x cubed, evaluated from 1 to 2. So my upper, 3 times 2 cubed, minus my lower, 2 cubed is 8, 8 times 3 is 24, so negative 1 over 24, minus a negative is the same as a positive, plus 1/3. Negative 1 over 24 plus 8 over 24 is 7 over 24, so this is convergent. Now I want to look at this graph, 1 over x to the 4th. This graph looks something similar to this. So basically, remember, integration is area. So I'm looking for the area underneath this curve from, let's say, 1 to 2. And that definitely looks like it's convergent, meaning it's bounded. It's not growing without bound. So this definitely looks like convergent is the correct solution for this. Well, let's look at the same graph, the same integral, but instead of going from 1 to 2, for this one, let's go ahead and look at our limit as we're going from, let's say, 1 to infinity. So again, 1 over x to the 4th dx. I'd still have my same technique of integration. Flip it up top, add 1, divide by the sum, so I get x to the negative 3 over negative 3, which is negative 1 over 3x cubed. And now I'm going from 1 to infinity here. Now, a lot of people will rewrite these before we even start the problem. They'll take this value of infinity and they'll rewrite with a limit out front before we even integrate. Just make sure you're not plugging infinity directly in. So my first one would be the limit as x approaches infinity, because it's my upper, of negative 1 over 3x cubed. And then I have my lower, which would be negative 1 over 3 times 1 cubed. Okay, so it looks like to me that this piece right here, the numerator is fixed, the denominator is increasing without bound. This is going towards 0. And why is that? Because the degree in the numerator is less than the degree in the denominator. That's kind of our important thing that we look at here. Now minus a negative is the same as a positive, 1/3. So I get 1/3. So this is convergent. Now this is an interesting idea. And the reason it's interesting is that area is always growing. So let's just look at this first quadrant, because we're going from 1 to infinity. So because we're going from 1 to infinity, this area keeps going on forever and ever and ever and ever and ever. So you'd think that this would be divergent. But what's happening is these incremental rectangles, remember we're adding rectangles here, are growing in area so slowly that they never go and get any larger past the value of 1/3. So another way that we could look at this is we could say, okay, I could find my area, and whatever my area is, I'd say plus 0.01 plus 0.001 plus 0.0001. You kind of get the idea here. It is growing, but it's not going to ever get above a particular value. The decimals are just going to keep going out and out and out. Now remember, this area is going toward 1/3. I'm taking a limit, so it's going toward 1/3. It's not exactly 1/3, but as we approach infinity, that area is also approaching the value of 1/3. So this is not divergent, even though this area that I'm looking at over here is continually growing without bound. It's not growing fast enough or adding enough area with my subsequent rectangles to ever go beyond the value of 1/3. So that's kind of an interesting idea. 1 to 2 is bound, 1 to infinity is still bound. Now kind of an interesting integral to look at is the integral of 1 over x dx. So let's take this one from 1 to infinity. Now remember, the integral of 1 over x dx, that's a 1 over u to u. So this is natural log absolute value of x evaluated from 1 to infinity. So my limits of integration will go natural log, actually it will be the limit, and make sure you write out these limits. Don't plug infinity directly in. Everyone will say you had the worst Calc 2 teacher ever if you do that. Minus the natural log absolute value of 1. So as x approaches infinity here, remember, this is your ln graph. As x approaches infinity, my y values are also approaching infinity. So this is equal to infinity minus the natural log of 1 is 0. This is equal to infinity, so this is divergent. Now why is this interesting? Well, why this is interesting is it's very, very similar to the graph that we just looked at. This graph is also up here in the first quadrant and down here in the third instead of the second quadrant as well. So this is going from 1, and then it's the same kind of shaded area, and it's going out toward infinity. Now 1 over x to the 4th diverged. Or I'm sorry, it converged. It converged to 1/3. This one is diverging. Now what's the difference? Well, the difference is how hard it hits the x-axis. This is going very, very slowly toward the x-axis. It's 1 over x. 1 over x to the 4th is going toward the x-axis very, very quick. So I am bounding the area faster. So it's really important that we look at this and we can see the difference. Even though the graphs are similar, this area keeps growing without bound, whereas the other one converged toward a particular value. So this one is divergent, the other one was convergent, even though they're very similar. Now I think I forgot to look at a discontinuity. I kind of got distracted by that neat comparison between 1 over x and 1 over x to the 4th. So let's look at the integral from, let's do -2 to +2 of 1 over x cubed dx. Now we already kind of have an idea what happened with 1 over x to the 4th. It was converging. 1 over x diverged. So let's see what 1 over x cubed does. Now I have a big problem here before we even get started. First of all, This is undefined at 0, and if you notice, negative 2 to 2 goes across 0. So I need to rewrite this. This is negative 2 to 0, 1 over x cubed. I'm going to flip this up top, x to the negative 3 dx, plus the integral from 0 to 2 of x to the negative 3 dx. Okay, so I have two different integrals. I'm going to have to treat these a little bit different. Now, let's think about our number line from negative 2 to positive 2, zeros in between. So this is my first negative 2 to 0 is right here. If you notice, I'm approaching 0 from the left, so we need to keep that in mind. Approaching 0 from the left. So another way to rewrite this would be the limit as a, I'll show you what a is here in a moment, as a approaches 0 from the left of the integral from negative 2 to a, so I'm replacing this 0 with this limit notation, x to the negative 3 dx, plus the limit as, let's say, b, because we don't want to use a again. Over here, this integral from 0 to 2 is right here. I'd be approaching 0 from the right. Okay, 0 from the right. So this would be 0 from the right, the integral of b to 2. So this is another way we could have rewritten the infinite ones as well, as we could have pulled that out front. So let's go ahead first of all and integrate. So we'll have the limit as a approaches 0 from the left, x to the negative 3, I would add 1 divided by the sum, so that would be x to the negative 2 divided by negative 2, evaluated from negative 2 to a, plus, whoops, I forgot the rest of this integrand over here, the limit as b approaches 0 from the right of x to the negative 2 divided by negative 2 from b to 2. Okay, so simplifying the limit as a approaches 0 from the left, this flips down negative 1 over 2x squared, negative 2 to a, lots to keep track of here. Can't drop my limit notation. Negative 1 over 2x squared, evaluated from b to 2. Okay, so let's go ahead and take those limits. So for this first one, I'm always going to plug in my upper first. So as a approaches 0 from the left of negative 1 over 2a squared, okay, and then here I'll have minus my lower, which would be minus a negative 1 over 2 times negative 2 quantity squared. So this is my first one. I'm going to work through this before I pick up my b over here. So as a approaches 0, let's think what this looks like. Negative 1 over 2a squared. If we plug 0 directly in here, we get negative 1 over 0, which of course is an undefined fraction. And if I have an undefined fraction, that basically tells me I'm going to either toward infinity or negative infinity. I'm not sure which. So let's look and plug in some values here. Negative 1 over 2a squared. The graph of negative 1 over 2a squared. Okay, so this is the graph of, let's say, positive 1 over 2a squared. So negative 1 over 2a squared will look something like this. Okay, so as we approach 0, so we're approaching 0 from the left, we can see this is going toward negative infinity. So this is equal to a negative infinity plus negative times a negative is a positive, or minus a negative is the same as a positive. 2 squared is 4, 4 times 2 is 8. So this is negative infinity plus 1/8. And we could stop there because as soon as I have infinity in anything here, I know that I'm going to have a divergent area. Okay, and then over here, the limit as b approaches 0 from the right. This would be the limit as b approaches 0. I guess I can write it up here. Plus the limit as b approaches 0 from the right of negative 1 over 2b squared. So there's my upper. Actually, my upper will be the 2. I have to plug that 2 in first. So that would be a negative 1 over 2 times 2 squared minus my lower, which would be the limit as b approaches 0 from the right of negative 1 over 2b squared. Okay, so this is going to be 2 squared is 4 times 2 is 8, so this is a negative 1/8 minus. Now as we approach 0 from the right, I already have the graph down here. This is also going toward negative infinity. So this is negative infinity plus 8. And so if we keep simplifying here, this becomes negative infinity plus infinity eventually, which is actually an indeterminate form. So this is one of the indeterminate forms we didn't go over, but this goes toward infinity, which means it diverges. Okay, so again, this was actually negative infinity plus infinity. It's an indeterminate form we haven't looked at, but it does go toward infinity in this particular case. Now, diverges, that means the area is growing without bounds. So let's go ahead and look at our original graph, 1 over x cubed from negative 2 to 2. So let's look at y equal 1 over x cubed from negative 2 to 2. So this is the graph of 1 over x cubed. Let's say from negative 2 we'll say is right here, and positive 2 is over here. So we're looking at this area, and we can see that what ends up happening here is this area is growing very, very fast as we come down in this direction. It's growing without bound. It's not going toward the y-axis fast enough to bound the area. So that is why this is divergent. So we've looked at a lot of different integration techniques so far this semester, also our techniques from Calc 1. So remember, when we're talking about improper integrals, the integration technique should be a little simpler. The actual evaluating the improper integral part is more of the focus here. But these problems are really neat because you can combine so many different things into one problem. Many different techniques of integration, also improper integrals, inverse trig functions at infinity. I mean, there's all sorts of great things to be able to do here. So these problems can get pretty long, and it's nice to be able to include a problem with several different steps in them. So those are the likely types of problems that you'll see on the handwritten homework and on your exam. Good luck on this section, and as usual, please let me know if you have questions. You can take a screenshot of the problem. You can set up online office hours, stop by my office if you're on campus, or of course we also have the Pearson Connect to a Tutor. Good luck!